Hello, welcome back. So today, we'll learn about rational functions. Our goals, as it says, understand and be able to identify the properties of rational functions, be able to find the domain and vertical asymptotes of rational function, and we'll see how they're related, and also be able to find what are called the horizontal oblique asymptotes of rational function if they exist. I don't have these, some do. Let's take a look at a rational function, the definition, like the official definition. Something looks like this, okay? So it's called some function, f of x, and it has to be a function. And basically where your numerator and denominator are both polynomials, okay? And also, because you can't divide by zero, then h of x itself can't be zero. We may have places where it's zero, but it can't be just itself zero. So that's kind of in general what a polynomial function looks like, a rational function looks like, where you have one polynomial divided by another. Remember, polynomial can even be a constant in some cases, or can be a constant. Now, first, what we want to do, kind of get the feel for these, is find the domain of a rational function. So let's go over and look on this side. Let's look at our first example. So we want to find the domain. All right, let's take a look at a basic example. So number one, our function is f of x equals 1 over x minus 1. Okay, so in general, your domain, you want to, or the values of x you can plug in. And for real functions, then basically you can't include anything that'll make it imaginary. It means you're dividing, you have like a negative under an even root, or it can't be anything that's going to make it undefined. And that's what we focus on here with rational functions. That's what's most likely to be an issue. So as it says, the domain of a function cannot include any values that will make the function undefined, and those values that make it defined will make the denominator zero. So to find these values, what we're going to do is take our denominator, set equal to 0, and solve. X minus 1 is equal to 0. If we do that, just add a 1 to both sides to get that x is equal to 0. Okay, what this x is equal to 1. Sorry, it's equal to 1. Now, what this means then, as basically this value will make f of x, our function, undefined. Okay, we can see that if you plug 1 in for x, it's f of 1, plug 1 in, we'd have 1 minus 1 equals 0. That would make it undefined. So basically, this value will make it undefined, and this value also can't be in the domain. It can't be part of the domain. Okay. Now, that's actually the only value that can't be part of the domain. So then our domain, if you want to think of it as a number line, so here's 0, here's 1. We have to exclude 1, it's an open circle, but we can include everything to either side of 1, the left side to the right side. So then our domain in words is just all real numbers except 1. But if you write it as an interval, it goes from negative infinity to 1. Let's give the 1 not included as an open circle. And then starting at 1, let's get 1 not being included to infinity. And then the union sign in the middle. So in intervals, that's a way of saying all real numbers except 1. So that's our domain. Okay, let's take a look at another example. And this time, let's say our function, let's call it f of x again. You can call it whatever you want. Let's say it's going to be just x over x squared plus 5x plus 6. Okay. Now, once again, the only problem we have our domain here is if we end up dividing by 0. Now, actually, the x here plays no part in that. The numerator does, just the denominator. So once again, we set our denominator equal to 0 and solve. So we want to solve x squared plus 5x plus 6 is 0. And in this case, this factors. So if it doesn't, you can always use the quadratic formula. This actually factors into x plus 3 and x plus 2. And then you set each one of these equal to 0 to find what make each one 0. And of course, it will give us negative 3 and negative 2. Okay. So based on what this says, then x can't be -3 and x can't be -2, or f of x will be undefined. Our function will be undefined if we plug those in. Okay, so if we do a similar thing, write out what our domain will be. Let's also do a number line to help us. Here's 0. Here's, I should have a little more space, but it's okay. -3 and -2. Once again, they're not, can't be included, so we have to put open circles. And so this time our number line is split into 3 parts. To the left, or what's less than -3, between -3 and -2, and then to the right, or what's greater than -2. And then our domain is an interval. And once again, in words, we just say all real numbers except -3 and -2. But our domain, this interval, is -infinity to -3, with -3 not included. Then the union of that from -3 to -2, oops, -2, neither one included either. And then once again, the union of this interval from -2 to infinity, and once again, -2 is not included. So that's our domain in this case. Okay, so that's how we find the domain. So basically, unless in most cases, these rational functions, because we also have polynomials, you're not going to have a variable under a radical sign. So you have to worry about that part, anything being imaginary. So you have a concern with things being undefined. Okay, now, some about vertical asymptotes. Vertical asymptotes are basically vertical lines where functions are undefined. Okay, so vertical asymptotes are vertical lines where functions are undefined. Okay, so the examples we just did a minute ago, if I have, f, the one I had a moment ago, first one, 1 over x minus 1, okay, has, it's called a vertical asymptote at x equals 1, okay? And the other one I did, f of x was equal to x over, you can write either the original way or this factored, x squared plus 5x plus 6. Okay, this case has two vertical asymptotes. Let's abbreviate those at x equals -3 and x equals -2. Okay, so wherever many places you have the functions undefined, you have vertical asymptotes there. Let's take a look at the graphs of these on Desmos. So we're going to Desmos, DESMOS.com. And so if we graph the first one, 1 over x minus 1, and you can see what happens here. But then if I graph the vertical line x equals 1, what happens is that, and as we'll see, a graph can never cross a vertical asymptote. What will happen is we'll approach it either from above or below and go toward infinity. And which direction it goes just depends on the particular function. Basically, we get as close as possible to the vertical asymptote. Okay, if we zoom out, we can see that it's getting as close as possible without ever actually touching it, because the graph never actually, we said our domain of this function is all real numbers except 1. So get as close to 1 as possible without ever actually touching it. And then it goes to either negative infinity or infinity close to vertical asymptote. Okay. Look at the other one we did. So we had x divided by x squared plus 5x plus 6. As we'll see, we have 2. And actually, probably need to zoom out there to see what happens. Yeah, so here's the rest of that graph. So we didn't see it at first, but let's get our asymptotes. Let's plot those. X equals -3 and x equals -2. Okay, and so what happens if we look, so it approaches a different way, definitely, but as you can see, it approaches both here and there. Okay, and it gets as close as possible those lines without ever actually touching it. That's what a vertical asymptote. So anytime you have a value that makes a function undefined, a vertical asymptote there, and the graph will approach it, we call asymptotically. That's why it's called that. And get as close as possible without ever reaching it, and will actually graph will go toward infinity or negative infinity at the asymptote, and which direction it goes simply depends on the function itself. Okay, so those are important part of rational functions to understand. Now, those are not the only kind of asymptotes we can have. We can also have what are called horizontal asymptotes. Let's talk about those. Let's see what this says. So basically, if the degree of the numerator is less than equal to the degree of the denominator, um, you have what's called a horizontal asymptote. The horizontal asymptote is simply a horizontal line. Okay. This is, oops. Is a horizontal line. Okay. And the graph approaches far from zero. So let's look at a few examples. Okay. And we can actually look at the ones we just did. All right. In part. So let's look at the one f of x. The one we just did is over x equals x squared plus 5x plus 6. Okay. Now here, the degree of the numerator is less than the degree of the denominator. Okay. So the degree of the numerator here is 1. That's the highest power of x, the numerator. The degree of the denominator is 2. That's the highest power of x, the denominator. Okay. So in that case, then you have a horizontal asymptote. I should say so. This implies a horizontal asymptote at y equals 0, which is the x-axis. Let's go back and take a look at the graph. And that's what happens. So if you notice here, the graph, it approaches the x-axis, in this case from below, in this case actually from above. But if you track this graph, you can get as close, as far as away from 0 as you want, and it will get close and closer to 0. Okay, it gets closer to y equals 0. The y coordinates gets closer and closer to 0 the further away from 0 we go in both directions. So that's what's called a horizontal asymptote. In this case, it approaches it from below, but still getting closer to the y coordinate, getting closer and closer to 0 the further from the origin we go. Now, one thing also to keep in mind is a graph can cross a horizontal asymptote as it does right here. Okay, at our intercept, it does that. But it can't cross, so a graph can never cross a vertical asymptote, but it can cross a horizontal asymptote, only close to the origin. Far from the origin, it doesn't cross it. Okay, just approach it forever. Approach it the same way a graph approaches a vertical asymptote, but just far from 0, far from the origin, it approaches a horizontal asymptote. Okay, now, what if we had a different function? So let's call this number 1. This number 2, let's make up 1. We have, let's say, f of x. Let's actually change this one somewhat. Let's make this 3x squared over x squared plus 5x plus 6. Okay. Now, what does that do? Well, here, the degrees in both degrees of the numerator and the denominator are the same. Okay. So in this case, we look at to find a horizontal asymptote, look at our leading terms. Okay. This looks like far from zero is going to look like far from zero. This looks like 3x squared over x squared. Okay, our leading term in the numerator and denominator, which of course is just 3 over 1, which is 3. Okay, that's what this says here. So if the degree of the numerator is equal to the degree of the denominator, your horizontal asymptote is actually what I'm calling an over bn, where a is the coefficient, the number in front of your leading term in your numerator, which is 3, divided by bn, where b is the leading term, is a coefficient of leading term in the denominator, so the number in front of the leading term of the denominator, in this case, which is 1. Okay. So that's what this looks like. All right, so let's take a look at that. All right, so if I just simply change the one I did to make this, instead of 3, let's actually get rid of, well, let's just make this 3 here. 3x squared. Okay. Now, you notice we still have the same vertical asymptotes. Those haven't changed. But now let's also put in a horizontal asymptote of y equals 3. As we can see the graph, once again, it can cross it. It can cross, you can cross a horizontal asymptote. In this case, this one does right here, the green line. You see, as we, the further we get, just to go with the green line, there we go. So the further I go out in either direction, the closer and closer I get to 3 without ever actually reaching 3. Same thing over here. If I go in this direction, the further I go from the origin, I get closer to 3, in this case from above, without ever actually reaching it. Once again, a graph can cross a horizontal asymptote far from, close to the origin, but it can't cross it far from the origin, far from 0. Okay. Now, what if we did something else? So let's actually make up another one. I'll just make it up right here and see what would happen. So what if we, well, let's just modify this. And what if we did this as, made this a 6? Let's graph that. Okay. So 3 over 6 would be 1/2. So let's make sure that we have, so we see, okay. So let's graph the line y equals 1/2. As we see, the same thing, okay. It approaches that line far from 0, okay. So we look at our leading terms, highest power terms, numerator and denominator, basically, and then those coefficients in front, in this case, 3 over 6 or 1/2 becomes our horizontal asymptote. Now, this is, we have a horizontal asymptote, so let's review. If your degree of your denominator is bigger than the degree of the numerator, like it is here, then you have your horizontal asymptote is the x-axis, y equals 0. If they're the same, if the degree of numerator and denominator is the same, then you look at your coefficients in front, okay, and that becomes this coefficient divided by that coefficient, then gives you the value of a horizontal asymptote. Okay. Now, what if the degree is larger? Okay. Well, then let's say, what if we had this? What if this was like x cubed? Then you have what's called an oblique asymptote. Let's talk about that. Okay. So an oblique asymptote, okay, if the degree of the numerator is 1 degree bigger than the degree of the denominator. Okay, that's what it says over here. Let's take a look. So oblique asymptotes. If the degree of the numerator is greater than the degree of the denominator by 1, then you have what's called an oblique asymptote. Okay, so let's take a look. Let's modify our example again. Okay. Let's say we have f of x is equal to 3x cubed over x squared plus 5x plus 6. Okay. So let's take a look at that. So this is one larger. Okay. We have x cubed over x squared. That's one larger. Okay. So it's called our oblique asymptote. Is going to be this time it's going to be a line, but not a horizontal line. It's actually going to be a line where the slope is basically given by these coefficients again. Okay. Where your slope of your line is given by this coefficient, your leading coefficient on top, divided by leading coefficient on the denominator. So it's a 3/1 times x, or y equals 3x. And that's called an oblique asymptote. So the graph will approach this line, y equals 3x, far from 0. Let's take a look and see how that happens. Okay, let's go back here. Now, let me actually get rid of some of these. Let's just modify this again. Let's go back to the original one and make this 3. Let's make this x cubed. Okay. Okay, there we go. Yeah, you have to go zoom out a bit to see it. And let's graph this line, y equals 3x. I was looking for, so you didn't see it right away. And also, like before, you can cross an oblique asymptote near the origin. But what happens is as we zoom out, we'll see it approaches that line. Far from the origin, is closer and closer to that line, as close to that line as possible. Okay, that's an oblique asymptote. So it's still a straight line, a straight asymptotic line, but it's not a horizontal line. Okay, and then once again, this happens if the numerator is one more than the denominator. So imagine let's change this. What if this was x to the 4th and this was x cubed? Okay, as long as it's one larger, we'll do exactly the same thing. Oops, 3rd, not 4, 3. Okay, yeah. So as long, yeah, so you can see here, the blue line is our oblique asymptote, the green line is our function. And as long as the degree of the numerator is one more than the degree of the denominator, the same thing happens, as we can see. Okay. Now, let's finish this up. So that's an oblique asymptote. Okay. Now, but if let's finish saying this. So if the degree of the numerator is greater than the denominator by 2 or more, there's no asymptote. Okay. So if the degree of the numerator is greater than the degree of the denominator by more than 2, no asymptote. So finally, let's do one more modification of this. So f of x is equal to, say this was just 3x to the 5th over x squared. I just 3x to the 4th. I don't need that. 3x to the 4th over x squared plus 5x plus 6. Let's do this and see what that looks like. And here, there's no asymptote. So let's go back to Desmos and graph that. So let me first get rid of this. Now, if I change this to, let's go back and change the 2. Of course, 3, as long as it's 2 or more. So let's make this 2. Yeah, here we go. We can see it's a little hard to see here. Tell that basically it doesn't approach any straight line. Okay, or if we make it even larger, like to the 5th, it makes that even more pronounced. Now, it doesn't approach this, so it no longer approaches a straight line far from 0. Okay, either one. So fifth, so anytime your degree of your numerator is more than 2 or more greater than degree of your denominator, it no longer approaches a straight line far from 0. Okay. So let's take a look now. If all these, we kept the denominator the same, so they'll have vertical asymptotes in the same places. Okay, even though the graph itself can change quite a bit as we've seen, but they all have vertical asymptotes in the same places. So you see one spot up here. So actually I bring my asymptotes back in. X equals -3 and x equals -2. A little hard to see. Let's see if I can zoom in on that. Let's see what happens. Yeah, basically, it's hard to see here, but basically the same thing is happening. So the function actually will never cross those lines, so it is really hard to see. Okay, so let's kind of summarize what we've done so far today. So we've seen are some behaviors of rational functions and what can happen. So if you have x's in your denominator, you often will have, almost in any case, every case, not every case, but almost every case, you'll have a vertical asymptote. That's where the function is undefined, and those points cannot be included in your domain. You have to exclude those when you write your domain. Okay, now, so you have vertical asymptotes where the function is undefined. Now, you have a horizontal asymptote if the degree of your numerator is less than the degree of your denominator. You definitely have a horizontal asymptote in that case at y equals 0. Now, if the degree of your numerator is the same as the degree of your denominator, you also have a horizontal asymptote. Basically, the line it becomes is this. It's a, actually I should include this. So not just 3, but y equals 3. Okay, approaches that line y equals 3. Base your leading coefficient in your numerator over leading coefficient in your denominator. It looks like that line, horizontal line. If you're, and once again, if they're the same, this can be both x squared, x cubed, x to the fifth are both the same, you have the same behavior. Now, if the degree of the numerator is 1 larger than the degree of the denominator, you also approach a line. It's not you approach a straight line far from the origin, just not a horizontal line. And basically, the leading coefficient of numerator over the leading coefficient of the denominator becomes the slope of that line. As y equals the slope, y equals then that slope then times x. And then finally, if the degree of the numerator is 2 or more greater than the degree of the denominator, there's no straight line asymptote. And also remember, a graph can never cross a vertical asymptote, but it can, close to the origin, cross horizontal asymptotes or oblique asymptotes. So those are some of the details of rational functions you need to make sure that you understand. Thank you. Have a good day.